Okay. All right. So this begins chapter 10, which deals with chemical reactions. Now, the last chapter, we introduced your first chemical reaction. That was the neutralization reaction between an acid and a base. And in that product, a proton and a hydroxide, when they combine, they produce water. So that was your first type of reaction. There's only 6 types that we're going to work with. Of all the chemical reactions out there, we're going to really only they're basically broken down to 6 types. There's what we call a combustion reaction. Anything that burns requires oxygen, just like your vehicle when you're burning the hydrocarbons in the gasoline. That's burning of hydrocarbons, which produces carbon dioxide and water. That's the second type of reaction that we're going to be talking about. Okay. Well, let's talk about this first. This is called the conservation of matter. Now, what exactly does that mean? Basically, matter is neither created or destroyed. The matter that we have on hand is what we got, and all we do is change the matter that we have into a different form. That's a chemical reaction. For example, you may be eating something that contains carbon integrated in some manner in whatever you're eating, and then you ingest it. That carbon is still carbon, still got 6 protons. When you eat that material with containing carbon, that material then is incorporated into your body. So that same carbon that was in that item that you ate now has been incorporated into your body. As we progress and we evolve and whatever in our daily lives, we produce byproducts. And one of the byproducts that we produce is carbon dioxide. We exhale carbon dioxide. So during that process of that carbon being on the material you ate, then it got incorporated into your body, then you metabolized it, and one of the products it got converted to now is carbon dioxide. So the carbon dioxide then, when you exhale, that same carbon that started off way in the beginning now is back in the atmosphere. That carbon dioxide could be absorbed, will be absorbed by, let's say, a plant material, because carbon dioxide, plants need carbon dioxide, obviously. Then that plant material then incorporates it into its body, its system in some manner. So that carbon is still carbon all the way in through the whole cycle, and it just gets regenerated over and over again and just gets converted. So matter is neither created nor destroyed. What we do is we just change it, which means that the total mass of reactants, when we react it, excuse me, will have the total mass of products. And so if I have A plus B to give me C, and A weighs 5 grams and B weighs 5 grams, and then our product C should have a total weight of 10 grams. In fact, we have means to verify that by having closed reactions that we can measure all the material. And sure enough, if we start off with 10 grams of reactants, we end up with 10 grams of products. Okay. We just simply, another way to state that is says, if you start off with, here the number of these 254 carbons, but you can start off with 1,000,000 carbons in a reaction. Well, when the reaction is completed, you're going to have the same number of carbon atoms. And not just not for carbon, but all the elements, whatever the elements are being utilized in the chemical reaction. Okay. And so we got to balance the reaction. Now, when we've been putting structures together to make formulas, we've been putting subscripts like sodium oxide, Na2O. Okay, we need 2 sodiums for every oxide. Okay, now that ratio is constant. We don't change the coefficient, the subscript. But if we need to display, say we need 2 molecules or two molecules of sodium oxide, then we put a 2 in front of the whole formula, the whole compound formula. And that tells us how many of those units we need. We can change that, we call that a coefficient. We can change that coefficient all, as many times as we need. We can't change the subscripts, okay? Remember that. If you need more of H2O, we put a coefficient in front of the whole formula. We don't change the subscripts. And so we have to balance the reaction, okay? And we'll have some examples about that, okay? So balancing reactions. Well, before we even can balance, we got to make sure that the formula that we put together is correct. And they're correct to put together the correct number of subscripts. And that's why I stated in the previous chapter that when we have for example, an ionic compound, we first write the ions. And so, for example, if we got to put together, let's say, calcium ion to make calcium chloride, Cl2, we have to recognize that the calcium ion is in group 2 and has a +2 charge. And we have to also recognize that the chlorides are in group 7, and when they become ions, they have a -1 charge. So when we put the formula together to make calcium chloride, we have to put them together in such that the charges cancel out. So we need 2 chlorides for every calcium ion. And hence the formula is CaCl2. Okay, so we got to be able to write the equation properly, the formula correctly. Excuse me. Then the last thing we do, once we write it all out, we have to balance it. So if I start to have seven carbons on the left side of the equation, I must have 7 carbons on the right side. Okay, for example. And so we start adding coefficients. For example, let's take a look at this example. This is a very common example. We're taking hydrogen gas and igniting it with oxygen. And the product that is produced is water. So the reaction is hydrogen gas in the presence of oxygen, and an ignition source will explode, because this thing will explode, and produce water. Now, if you notice, there's a 2 coefficient in front of hydrogen. That tells you that there are 4 hydrogen atoms, okay? Which means on the product side, we must have 4 hydrogen atoms. So that 2 coefficient in front of the water, H2O, that applies for all the atoms in H2O. So we have 4 hydrogens on the right-hand side. The hydrogens have changed. It's still hydrogen. It's still the hydrogen element. But in the reaction side, it's the hydrogen gas. On the product side, hydrogen has been converted to be incorporated into the structure of water. Okay. If we look at oxygen as a reactant, it's a diatomic. Both of these, hydrogen and oxygen, are diatomic. That's why the subscript. So oxygen, there's 2 oxygen atoms as a reactant. And as a product, there's that 2 coefficient in front of water that tells us there are 2 oxygens. Okay. And so it's broken down, it's shown like this. Kind of, instead of having to write all the structures, that's what the coefficient comes into play. So you can see we got 2 hydrogens, diatomic hydrogens. Let me make sure I got the right one right here. Okay, a total of 4 hydrogen atoms. Over here on the product side, we still have 4 hydrogens. They're denoted by the dark color. Okay, but they're in the form of water. They're incorporated into water, but there's still 4 of them. And then oxygen is the reactant side, that denoted by the white spheres. There's 2 on the left-hand side. Okay, and as products, there's 2 oxygens in the form of water. And so hence, that's why we put a coefficient in front of H2O to tell us there's 2 molecules of water. Okay, so this reaction is what we classify as balanced. Now, The thing, once you balance it, it's very crucial that we balance it correctly, because we're going to use this information when we start doing calculations. And so now take a look at the coefficient. 2 hydrogen molecules per 1. If there's no number in front of the molecule, it's understood to be 1. So the ratio is 2 to 1. Okay? It's and that ratio, like we talked about back when we were converting units, it's simply, I can write that ratio one or two ways. Okay? And let me do that here. So that means that I could say 2 hydrogens, write it with hydrogen, and this is a subscript, the second 2, divided by O2. I can write it like that, or I can put the O2 in the numerator, okay, and 2 hydrogen molecules, like, okay, so that's a ratio. And so we can calculate, use that ratio like we did in the conversion factors to do calculations, okay? All right, so let's move on. Let's balance this equation. This reaction is nitrogen gas in the presence of hydrogen gives you NH3, otherwise known as ammonia, okay? So notice that as a reactant, we have 2 nitrogens, but as a product, we only have 1, okay? Furthermore, hydrogen as a reactant, we only have 2, and we only have 3 as a product. So this reaction is not balanced. Now, some of these reactions, I will give you some tidbits on how to balance them. However, there's some that there's no little kind of set way to do it. It's basically trial and error. This is one example of those. But the other reactions are more, we have a more systematic approach. Fortunately, the reactions you're going to be balancing are not going to be very complex. It'll be something like this. Okay, so analyze that reaction and you say, well, wait a minute. I got 2 nitrogens. What if I put a 2 in front of the ammonia, NH3? That certainly would balance my nitrogens. And then what happens? That would increase the number of hydrogens to 6, right? And so if I put a, let me see if I can do that. If I put a 2 in front of ammonia, did you see how that increases now the number, or that now balances the nitrogens? But now it increases the hydrogens to 6 now. No problem. What if I go back to hydrogen right there, and maybe I put a 3 there? Okay. Let's take a look at that. Now I got 6 hydrogens as reactants, 6 hydrogens as products. I got 2 nitrogens as a reactant and 2 nitrogens as ammonia. Looks pretty balanced. Okay. Let's clear that. And sure enough, we got a balanced chemical equation. Once you balance it, look at the ratio between reactants. 1 nitrogen per 3 hydrogens. Also looked at the ratio between reactants and products. That means 1 nitrogen molecule per 2 ammonia, or 3 hydrogen to 2 ammonia. Those are ratios you can use if necessary. Okay. All right, we have another one here. This one is a hydrogen gas in the presence of bromine gives us hydrobromic acid, HBr. Okay. This one's pretty straightforward here now, because I got 2 hydrogens as reactants and 2 bromides as products. So if I put a 2 in front of HBr, guess what? It's totally balanced. Okay. Now look at your ratios between reactants. It's a 1-to-1, 1 hydrogen per 1 bromine. From hydrogen to HBr, it's a 1-to-2. From bromine to HBr, it's a 1-to-2. Okay. All right. Here, maybe a little more challenging, but we'll see. Excuse me. Okay, so we got carbon monoxide in the presence of oxygen to give you carbon dioxide. Okay. Now, take note of me when I'm telling you the reaction, because sometimes you have problems that you need to work where they actually write out the equation. In other words, what I just stated, carbon monoxide in the presence of oxygen reacts to give you carbon dioxide. Given that statement, then you convert it to an equation as is written here. So be able to go from the words to the reaction, or the reaction to the words. Okay. And so if we look at carbon first, we can see that carbon is balanced. We got 1 in each side. There's a little bit of disparity with respect to oxygen, because we've got 3 on the left side as reactants and 2 on the right side. So you might have to analyze that a little bit and say, hey, what if I put a 2 in front of carbon monoxide? Okay. If I put a 2 in carbon monoxide, and let's do that. Let me see if I can do. Let's say if I put a 2 there, okay. Well, now that gives me an even number of oxygens. Now I got 2 oxygens in carbon monoxide and 2 in oxygen. But it increased my carbon. So what if I go back now to balance my carbon and I put in a 2 in front of carbon dioxide? Okay, kind of moved in a little bit, but you can see what I'm trying to do there. And so now go check it. I got 2 carbons as reactants, 2 as products, 4 oxygens total is reactants, and 4 oxygens as products. So it looks pretty clear, balanced there. Okay, so now we have a balanced chemical equation. When you are balancing, sometimes you start off with the reactants and add a coefficient. Sometimes you start with the products and add a coefficient, and then go back and forth. You go back and forth. Reactants, products, reactants, or vice versa, whichever. But you go back and forth to get everybody balanced, okay? And then we look at that ratio. The ratio is 2 carbon monoxide per 1 oxygen. So it's a 2-to-1. The ratio between carbon monoxide and carbon dioxide is a 2-to-2 or 1-to-1, equal ratio. And from oxygen to carbon dioxide is a 1-to-2 ratio. Okay, well, now we're going to take words and convert them to reactions. Okay, and remember to include the physical states. Okay, solid, liquid, gas. And aqueous if we're talking about ionic compounds and that are soluble. Okay. Now you might say, well, how do I know if it's a solid, liquid, or gas? Well, for the elements, recall that we had a periodic table. We had a table that showed you which ones were gases and which ones were solids and which ones were liquids. Okay. And when we deal with aqueous, normally what we're talking about is ionic compounds of metal and non-metal that are soluble in water, which is based on the solubility rules. You notice we're getting all this information, kind of bringing it together here. If the ionic compound is insoluble, remember we put S for solid. Okay. So remember which are solids, liquid, and gases. Also remember which are diatomic. There's only 7. Okay. Excuse me. Excuse me. I had to sneeze. Okay, remember which are diatomic. There are only 7 elements that are diatomic. Have no fear of ice cold beverage. Okay. So go back and refresh that. And then remember that the subscripts are what we put together. We don't change the subscripts. Okay. If we need to add more molecules, then we change the coefficient. The coefficient is that the number in front of the formula. We could change that all we want. Okay. So let's take this example. It says here the reaction, sodium reacts with chlorine to produce solid sodium chloride. Okay, let's break down that sentence. Okay, and so the reactants are, let me do something here. It says sodium reacts with chlorine. Okay, now the key word here is sodium. They didn't say sodium chloride, sodium bromide, they just said sodium. So that infers that we're talking about the element sodium. Then it says reacts. The reacts tells you that's a plus sign. So sodium plus chlorine, note the suffix ine, which means it's the element. They didn't say chloride, they said chlorine. And so we're dealing with the elements of sodium and chlorine. Then they tell you it produce generally is a key to tell you that's the arrow pointing from left to right. Okay. To produce, and then they tell you solid, which is the physical state. And then we got sodium chloride. Okay. And so they're talking about nothing aqueous here because they tell you solid sodium chloride. Right? Otherwise, they would have said an aqueous solution, and then we would have used the physical state of AQ. Okay. So then, once we know that, the other aspect to remember that chlorine is one of the diatomic molecules, and so we need to write down the reaction as follows: sodium plus reacts, which is plus, reacts with chlorine, which is diatomic, to produce, which is the arrow, solid sodium chloride. Okay, so we've written the reaction. Now we got to add the physical states. We know that sodium is solid. Okay, we know that chlorine is one of the gases. Why? There's only a handful of gases. Refer back to the previous chapter. And then sodium chloride is solid because you've been told that. Okay, so we added the states. Now we're going to balance it. Now you can see we got 2 chlorines as a reactant, but only 1 as a product. And so we could easily put a 2 in front of sodium chloride. Okay, and let's do that. If we put a 2 in front of sodium chloride, that then balances the chlorides, but then the sodium is increased by 1 over here by 2. There's 2 sodium. So we come back to the reactants and we put a 2 in front of sodium metal. No, that didn't come out good, but you can see what I did there. Okay, now we have a balanced chemical reaction. Okay, which is 2 sodium for 1 chlorine to give us 2 sodium chloride. Okay. This is a fascinating reaction because sodium element is very reactive, and chlorine's a gas. And when they react together, you make something you can put in your French fries. Yeah. And all what happened was 1 electron got transferred, 1 tiny electron. Okay. So, I'm on the slide. You should take a look at that reaction. I don't think it's functional from where I tried it earlier. From my end, there's a problem. I don't know, but if you look at that link on your own time, you can see this reaction proceed. It's a pretty vigorous reaction. Okay, but the problem says aluminum reacts with bromine to produce solid aluminum bromide. Again, we break it down. Aluminum, all by itself, the word is the element. Reacts is plus. Bromine, again, is bromine, so it's diatomic, so it's Br2, reacts to produce aluminum bromide. So you break down the aluminum bromide to make sure first that you have sufficient, you put that formula together. So what do we know about aluminum when it becomes ionic? What is the charge of aluminum? Okay, it's a group 3 element. It's a metal. So is it going to gain or lose electrons? Anybody want to try? Would it have a plus or a negative charge? It definitely will have a plus charge. Specifically, what's the magnitude of the plus charge? It's in group 3, exactly. So it will be a +3 charge. And then the bromide, notice the term IDE tells you, okay, we're talking about the ion. And so it's a group 7 element. When it becomes an ion, it becomes a -1. Okay. So that means that we need 3 bromides for every aluminum ion. And so our formula would be AlBr3. Okay. So we write that down, AlBr3. Okay, then we want the physical states. We know that aluminum is a solid. Based on that periodic table we had, shows all the solids, liquid, and gases. We know from that table that bromine is a liquid. Okay. And we know that aluminum bromide is a solid because it gave it to you in the word problem, solid aluminum bromide. Okay. Remember, there's only 2 liquids of all the elements, mercury and bromine. Okay, so now we have it balanced, not balanced here, but we have the formula. Okay, so now we got to balance it. We got 1 aluminum reactant, 1 aluminum product, 2 bromines as a reactant, but 3 as bromides as a product. Okay, and so we got a 2 to 3 ratio here. So what if I put a 3 in front of the bromine and put a 2 in front of the aluminum bromide? So let's do that. Okay, let's put a 3 in front of the bromine and put a 2 in front of the aluminum bromide. That balances out the bromines. We have 6 total on both sides. But in putting that 2, that increased in my aluminum, but no problem. Now we go back to reactants and put a 2 there. Oh. And now we have a balanced chemical reaction. Okay. Two aluminums to 3 bromines to give us 2 aluminum bromides. Okay. Note the ratio between reactants, 2 to 3 between aluminum and bromine. And the ratio between aluminum and aluminum bromide is a 2 to 2 or a 1 to 1. The ratio between the ratio between bromine and aluminum bromide is a 3 to 2. Okay. So every time we balance an equation, note the ratio because we will eventually use that ratio to do calculations. Okay. So first, when you first write the reaction, write them in proper formulas, and once it's done, the subscript is set. Now you just add coefficients, and you go left and right, left, whatever you need until you got the right coefficients set up. Okay. Now, if, for example, you are doing the balancing and for some reason you come up with, let's say 4 there, 6 there, and 4 there. Okay, let's say you come up with those coefficients. It's still balanced, okay? But always reduce it to, like the term used in mathematics, reduce it to the lowest terms, so that 4 for aluminum can be brought down to 2. Everything is divisible by 2 here. So bring it down to the lowest coefficients that you can get. Okay. All right. Here's another reaction. The reaction of phosphorus reacting with oxygen to make diphosphorus pentoxide. Okay, now we're making, and previously we've been making ionic compounds, but we're making a covalent compound. Okay, and so we know the formula for phosphorus, or the symbol, I should say, because they're saying just phosphorus, so that's the element, so that would be P. They said reacting, which is the plus, with oxygen. Okay, the term oxygen automatically infers O2. Okay, and then to make is the key word to tell you that's the arrow from left to right, solid diphosphorus pentoxide. Okay, well, let's write the formula for diphosphorus pentoxide and break it down. Okay, the parent name is phosphorus and oxide, so it's P and O. Okay, that's the parent name, phosphorus and oxide. Then we look at the prefixes. Di means there are 2 phosphorus, and pentoxide tells us there are 5. Remember the prefix pent means 5. So the formula for diphosphorus pentoxide is P2O5. Okay, so now that we got the formula, we can write the equation as so. Okay, and now the next stage would be the states. We know phosphorus is a solid, oxygen is a gas, and diphosphorus pentoxide is a solid because it's given to us as a solid. Okay, so we got the physical state set up. Now we're going to balance it. Couple ways. There's no set way that's wrong or right. It's just a matter of trying to figure out, okay, what can I do here? I tend to work with the oxygens first. Okay, you can try with the phosphorus first. That will work. That's okay, whichever works for you. But first thing I noticed is, just like a previous one where we had it was the aluminum bromide, we had a 2 to 3 ratio. We got to look for a common factor. Okay, and notice that here and here it's a 2 to 5. So what if I were to put 5 in front of oxygen? Now, it didn't come out good, but it's 5 in front of oxygen and a 2 in front of diphosphorus pentoxide. That would balance out my oxygens. Okay, that means I got 10 as reactants and 10 as products. Putting that 2 in front of diphosphorus pentoxide now increases my phosphorus to 4. No problem. Now we go back to reactants. We'll put a 4 there, and we're balanced. Okay, let me clear it. So we have 4 phosphorus requires 5 oxygens to give us 2 molecules of diphosphorus pentoxide. So the ratio between reactants is 4 to 5. Okay. And the other ratio between phosphorus and diphosphorus pentoxide is a 4 to 2 or 2 to 1. And the ratio between oxygen and the product is a 5 to 2. Okay. All right. Now, this is something you may want to try at home. I'll let you try it, and we can bring it back and work on it. But here they're telling you nickel 3 sulfate plus, which is the plus, lead nitrate, lead 2 nitrate produces, which is the arrow, nickel 3 nitrate, and solid lead or solid lead 2 sulfate. Okay. First thing to do, I recommend, is to write the formulas for everything, given what you're given. That way you have the correct formula written up. Sulfate, nitrate, those are the polyatomic ions that you find in the table. So use the polyatomic ion table to make sure you select the correct polyatomic ion and note their charges. Okay, so put the formulas together and write your equation. And this is another type of reaction we're going to talk about. But notice one of the products produced is solid. Okay, it's solid because lead 2 sulfate is insoluble in aqueous solution. Okay, and the nickel 3 nitrate is soluble. So this is a different type of reaction. We're going to talk about this types here pretty soon. Okay, so try this at home. You should get that. Okay, and one key about these type of reactions to help you out, follow the polyatomic ions to get in balance. Okay, follow the SO4, follow the NO3 to get in balance. If you follow those and get those balanced, everything just falls into place by itself. Okay, because you start off with 3 SO4s on the left side, you should have 3 SO4s sulfates on the right side. Okay. All right, so give that one a try on your own and see if you can work it through. The answer is there, but see if you can work it through on your own. And if you're having a challenge with it, we can bring it back here and we can work it. Okay. All right, because that one here is, if you got this one worked out, the other ones you're going to be doing will be a piece of cake. All right. So let's talk about the 6 types of reactions. Okay. There's a type called combination. And just by the word itself, it's what it does. It combines. A general example is A plus B coming together to create AB, whatever AB is. Okay. All right. Second type is a decomposition. It's really the opposite of the combination, where you're taking some compound, in this case, general formula, generic example, ABC, and you do something to it and you break it into these components. Okay. An example of this would be, let's just take we did one earlier for combination where we took hydrogen plus oxygen to give us water. That's a good example of a combination reaction. Okay, hydrogen, oxygen gives us one product, H2O. Decomposition, we can take water, H2O, and we can undergo electrolysis and break it down, go the opposite. We put energy into the system, we take water, we break it down to make hydrogen and oxygen again. Okay. Now, Combustion. The key thing about combustion here, the ones that you only have to worry about is a combustion with what are called, and I mentioned these before, where is it? A hydrocarbon. I'm circling it right now. The X and the Y, the subscripts, are numbers. The smallest X can be is 1, and the smallest Y can be is 4. Okay. These are carbons, what we call hydrocarbons, and gasoline is a hydrocarbon. It's compounds made up of nothing but carbon and hydrogen. Well, in the presence of oxygen, for a combustion reaction, for anything to burn, we need oxygen. We all know that, right? We're going to burn something without oxygen, it's not going to work. Okay? So when you do a combustion reaction of a hydrocarbon, you're only going to get 2 products. That is carbon dioxide and water. Okay? That's it. Those are your products. So that's what's happening when you're driving your vehicle and you're burning the fuel. You are creating carbon dioxide and water. In fact, if you're ever in front of a vehicle and you see their tailpipe, sometimes you'll see a little liquid coming out of their tailpipe. That's what's coming out. Water is coming out. Now, our engines are not 100% efficient. Therefore, we are also making carbon monoxide. So, but we're going to pretend we're in the ideal world, and the combustion of a hydrocarbon produces only carbon dioxide and water. And we have a little technique to balance these reactions. When we get to balance these, I'll show you. Okay. The next type is called an acid-base reaction. We talked about that last chapter, where you have a acid, which normally it's written with the H in front. So it could be hydrochloric acid, it could be acetic acid. Okay, so if we have an acid reacting with a base, okay, and that's anything that produces a hydroxide ion. And when the proton and the hydroxide combine, guess what they make? They make water, H2O. You are neutralizing the acid in the base. And then the corresponding metals combine to form, in this case, Ma, whatever metal it may be, okay? Na, whatever anion. So normally the cation of the hydroxide, the base, and the anion of the acid combine to form Ma. Okay. One more. Now, we have another one called single replacement reaction. Okay. In this scenario, we have a metal. It's excuse me. Denoted here by the letter M. And then we have a ionic metal different than M. Hence, we denote it by AX. It's an ionic compound, metal and nonmetal. And what happens is the elemental M displaces the A, okay, to generate the new organic ionic compound MX. Then the A that was ionic now is back to an element. Okay. Classic example of this is plating. You may have some jewelry that has been plated. Your I don't know, you had any chrome plating on your vehicle or bicycle or something like that. This is a classic example. Now, how this is going to work? Well, let me send you back to our periodic table. Okay. Here's our infamous periodic table that we really rely on on it quite a bit. Okay. On the periodic table, right above the solubility rule, we have what is called the activity series. I just highlighted it with the blue box. Okay. What that tells us is which metals are more reactive. So if you look at the list, you see on the top, there's two layers. Only they've been normally would be squished down to one layer, but because of size, it's two lines. The very first metal is lithium. And what that tells you is that lithium is more reactive than potassium, which is more reactive to barium. And if you keep going, the least reactive uh, element here is Au, gold. Okay. Gold is very unreactive. It can react, but it takes vigorous conditions. All of this is relative to hydrogen gas. Okay. And so for this type of reaction to proceed, the way we write it, we use the activity series to determine which is the most reactive metal. And then we ask another question, and then from there we can determine whether that reaction will proceed or not. Okay. And we'll come back to that, but we're going to be using the activity series on that. Now, the next one we call a double replacement reaction. That example I gave you earlier, that try-at-home example, this is what it's called, a double replacement reaction. What generally means that when you start off this reaction, the reactants, if we look up the solubility of the reactants that I just highlighted here, they're all soluble. Okay. And using the solubility rules, they're all soluble. Now what happens is all they do is exchange partners. M1X now becomes M1Y, the anion of the other one. Now, if one of these is, let me change if one of these, for example, what I circled here, based on the solubility rules, is insoluble, then we got a reaction. Okay. Notice that previous example, they told you solid, whatever that product was. That implies that there was a reaction. Now, how do we determine whether a reaction proceeds? Okay. Guess where we go back? Back to the solubility rules. And so we put these together, there are two reactions together, okay? Exchange of partners, then go to the solubility rule and find out which one is insoluble. If one of the products is insoluble, then we got a reaction to proceed. And then we put S, solid, we got a reaction. If both products are soluble, then we got no reaction. Okay. So the double displacement reaction is driven by the solubility rules as to whether you get a reaction or not. Okay. So we have combination reaction, decomposition reaction, combustion reaction, an acid-base reaction or neutralization, a single replacement reaction, which is governed by the activity series, okay? And then we have a double replacement reaction, which is governed by the solubility rules, okay? All right, so those are the 6 types of reactions that we're gonna deal with. All right, so we have this example. We have phosphorus reacting with oxygen to give us diphosphorus tetroxide, okay? Then we got to balance it. Okay, so we can put a 2 in front of the oxygen that balances off our oxygens, and then that means then we got to put a 2 in front of phosphorus to balance the phosphorus. And so now we have a balanced chemical reaction here. And this example is a combination reaction. 99% of the time, the reactants are the elements for a combination reaction. Okay, so recognize that you're dealing with elements to give you some type of compound, in this case, a covalent compound. Okay, a decomposition reaction. It is where you have one reactant, normally a compound, okay? Then you do something to it, and you generally create the elements as products. This is iron 3 oxide, which is otherwise known as rust, okay? You can take that, heat it pretty high, and regenerate the iron, and it gives off oxygen. So this is an example of a decomposition reaction. Okay, now we got to balance it. Now you can follow the oxygens here. Notice that there's 3 oxygens in the iron 3 oxide, and 2 as a product as oxygen. So I can probably do a 2 in front of iron 3 oxide and a 3 in front of oxygen. That balances out my oxygens. For example, let's do that. If I put a 3 there and a 2 there, that balances out my oxygens, okay? Which then kicks up my iron to 4, so I can probably put a 4 here, okay? And that looks like it's balanced. Yeah, sure enough, okay? Decomposition reaction. Okay, combustion reaction. Okay. Here, that's a C3H8. This is the formula for what we call propane, which is a hydrocarbon. It's made up of nothing more than carbon and hydrogen, okay? So a combustion reaction requires oxygen, and the products, recognize that the only products you get for carbon dioxide, at least for Chem 130, is carbon dioxide and water, okay? So you're given the formula, you know it's a combustion because they're telling you it's combustion, so you need oxygen as a reactant, and then the only 2 products are carbon dioxide and hydrogen, okay? So you're right, there's your reaction. Now, here's some rules to balance combustion reactions. That's a little guideline, okay? So there's an order of balancing first. First, balance the carbons, okay? So balance the carbons, and then balance the hydrogens first, and then balance the oxygens. So proceed with that sequence, and you will have it. Let me back it up for a second. Okay, let's follow that sequence. Balance the carbons. We got 3 carbons as a reactant, so we need to put 3 in front of carbon dioxide. So hopefully I got enough room here to put a 3. Okay. All right, so then next we balance the hydrogen. Well, in propane, there's 8 hydrogens as a reactant, and there's only 2 as hydrogens in water. So to make 8, we put a 4 in front of water, okay? I apologize for my 4 there, but hopefully you get the gist of what I'm trying to do, okay? Now we balance the oxygens. All right, so on the left-hand side reactants, we only have 2 oxygens, but we have 6 coming from carbon dioxide, and 4 coming from water. So 6 plus 4 is 10, right? So we can put a 5 in front of O2, and guess what? You're balanced, okay? So for combustion reaction of hydrocarbons, you know that oxygens is a reactant, so that's something you got to put in first as a reactant. And you know that the only 2 products for hydrocarbons are carbon dioxide and water, okay? And to balance them, balance the carbons first, then balance the hydrogens, okay? And then at the end, balance the oxygens. And then it should be balanced. So in this case, the ratio of propane to oxygen is a 1 to 5. Okay, and then note the other ratios too, so we can actually calculate. These ratios are important in chemistry. Whether we do this reaction in the lab and maybe only working with like 10 grams, or if we're working with 10,000 kilotons, it's the same reaction. Okay, whether we do it in industrial scale or in the lab scale, that same ratio is true. Obviously, we're going to be working industrial scale with greater amounts, and that's where the chemical engineer comes in. The chemical engineer is the person who figures out how am I going to move 10,000 pounds of liquid from point A to point B. If I'm the chemist, we're in the lab, I might just have to move 10 grams from point A to point B. Totally different. All right. So that's a combustion reaction. And these are the rules are the guidelines to help you balance combustion reactions, okay? Carbon, hydrogen, and then do the oxygen last. Now, neutralization reaction. We introduced that last chapter, okay? Where we have an acid, denoted here by the general formula HA, reacting with the base, denoted by the general formula M, M being the metal hydroxide. You always get water all the time, and then the corresponding salt, depending on what the metal and the non-metal were when you first started. Now, to balance the reaction here, okay, follow the hydroxides and the protons, okay? And so here's the hydroxide, here's the proton. Note for barium hydroxide, there are 2 hydroxides. That tells you that you need 2 protons. So you can automatically put a 2 in front of HCl, which tells you that you're also going to make 2 H2Os, okay? And then the salt here, barium, it's a +2. Barium is in the group 2 element. So it's going to be an ionic form of +2. We know the chlorides are -1. So that means the salt, in this case, the Ma right here, for this example, will be barium chloride. And its formula would be BaCl2. Okay. All right. So we put two protons because we have 2 hydroxides, which means we get 2 waters, and then the barium chloride just falls into place. Check your balance. See if you're balanced. I have 2 hydrogens from HCl, 2 hydrogens from hydroxide. That's 4 hydrogens. I got 4 hydrogens on the product side as water. Okay. I got 2 chlorides as reactants, 2 chlorides in barium chloride. I got 1 barium, and I have 2 oxygens, 2 oxygens. Guess what? We're balanced. Okay. We're balanced. Now, here's the next one. A little bit more challenging, but that's okay. we can work it through. Recognize that we have an acid, H3PO4. Okay, here we go with the hydroxides again. Calcium hydroxide, otherwise known as TUMS. Okay, now in this case, I have 2 hydroxides in the calcium and 3 protons. Okay, so I need to balance these out. So I need enough protons and enough hydroxides. I need a common number. And guess what? The common number is 6, excuse me. So if I put a 3 in front of calcium hydroxide and a 2 in front of phosphoric acid, my hydroxides are balanced out. And my protons are balanced out. Okay? Which means that I'm going to make 6 waters. Am I not? I got 6 hydroxides, 6 protons. I'm going to make 6 waters. And then the corresponding salts come into play here. Calcium phosphate. All right. And we have automatically falls into play. I mean, as far as the salts are concerned, keep it in mind that you write them in ion form first before you put them together. And again, their calcium phosphate needs a common charge, which is a 6 again. So it becomes 3 calciums and 2 phosphates. Okay. And 6 waters are produced. All right. Now, ask the question here, why, and then I'll stop it up here. Why did we put a solid for calcium phosphate? Anybody know why that would be the case? Is that correct? By me putting the physical state as solid. Any idea? Exactly. It's insoluble. All phosphates, you go to solubility rules, all phosphates are insoluble unless they are combined with lithium, sodium, potassium, and ammonium, the big 4 in number 1. Okay. And obviously calcium is not one of them, so it would be insoluble. All right. Okay. Well, guys, let me stop it here. I got 3:06. I did go over a little bit. And any questions, comments, concerns? Let's stop the share. And